Here I'll set forth the equations that describe conservation of momentum in a two-body collision between, say, mass A and mass B, both able to move. We'll assume the system of masses A and B is isolated from time 1 to time 2, meaning that the net external impulse imparted to the system over that time interval is 0, in which case the momentum of the system would be constant. First, let's look at this from not from a system perspective, but just from like a two individual object perspective with Newton's third law relating the forces those objects are experiencing. So the change in momentum of object A, just object A, not the system, but change in momentum of A depends on the net force on A during that interval. So this would be the impulse imparted to A. And if the system is isolated, then the net force on A, or the impulse on A, will be just due to the force on A due to B. This is the internal force of B pushing on A. Likewise, we could write that the change in momentum for B will be due to the impulse imparted to B, and if our system is isolated, that will be solely due to the force on B due to A. That from A pushing on B, so the internal force here. And by Newton's third law, the force on A due to B is equal and opposite to the force on, did I say that right? The force on B due to A is equal and opposite to the force on A due to B at all times. So we can make that replacement and then note that these two expressions here are equal and opposite. Therefore, the change in momentum of B is equal and opposite to the change in momentum of A. Okay, so delta PA is equal and opposite to the delta PB. Any change in momentum that occurs is strictly a transfer of momentum between A and B. Whatever A loses, B gains, and vice versa. And since this is a vector equation, we see that momentum is conserved component-wise. Whatever change in x momentum A experiences, B experiences an equal and opposite change in x momentum. And likewise, whatever y momentum A gains or loses, B also gains or loses that amount of y momentum, separately conserved in the x and y direction. So really, this conservation law is three separate conservation laws, one each for the x, y, and z directions. We could express this in terms of masses and velocities if you prefer that. So delta PA is PA final minus PA initial equals the opposite of PB final minus PB initial. I can replace each of those momenta with mass times velocity. So MA VA final minus MA VA initial equals, and this on the right-hand side. And I can factor out that mass A from both these terms and factor out the mass B from both these terms to express it as mass A times VA final minus VA initial equals the opposite of mass B times VB final minus VB initial, or our conservation law here could be rewritten like this. We could say that mass A times the change in velocity A equals the opposite of mass B times the change in velocity B. And it's a vector equation, so really we'd express it as a separate equation for each of the x, y, and z directions. MA times delta VAX equals opposite of MB times delta VBX, and a separate equation for the y direction. You must not mix up x and y or combine x and y. They are separately conserved, each in their own separate equation. Okay, we can re-arrive at those ideas from a slightly different perspective if we start from the system perspective, thinking about our system, in which the momentum of the system is expressed as momentum of A plus the momentum of B. So the change in the momentum of the system is given by the change in momentum of A plus the change in momentum of B. And we're going to say that that will be 0 if that net external impulse is 0, if our system is isolated. And therefore, since the sum of the changes in the momentum of A and B is 0, we arrive again at the conclusion that the change in momentum of A equals the opposite of the change in momentum of B. There's a momentum transfer. Whatever A gains, B loses, and vice versa. If instead of expressing the conservation in terms of changes, you would prefer to express it in terms of initial equals final, we can do that. We can say that the initial momentum of the system equals the final momentum of the system if we're meeting this condition here. So momentum A initial plus momentum B initial, that's the total momentum initially, equals momentum A final plus momentum B final. That's the total momentum at the end. And that's a vector equation. So very often when we're actually solving a two-body collision, we're going to write down these equations here. This would be a common way for us to do it. We might write that PA1x plus PB1x, initial x component, equals PA2x plus PB2x, final x component. And likewise for the y component, likewise for the z component, if there were one. If we want to write this in terms of masses and velocities, we can do that. Just replaces each momentum with mass times velocity, and we get this. MAVA1 plus MBVB1, that's initial total momentum, equals MAVA2 plus MBVB2, final total momentum. And component-wise, that would be three separate equations, one for the x direction, one for the y direction, and one for the z direction. So conceptually, the essential conclusion for us here is that in a collision, each component of the momentum of the system cannot change, meaning we can neither create nor destroy x momentum nor y momentum. X momentum, or the x component of the momentum, can only be transferred between A and B in a way that keeps the total x momentum of the system constant. So whatever x momentum A loses, B gains. Momentum is conserved component-wise. So if the momentum of the system is constant, that means the x component of the momentum of the system is a constant. And the y component of the momentum of the system is a constant, potentially a different constant. These are not the same three constants, but each one of these would be held constant. Likewise for the z component of the momentum. And you cannot convert x momentum into y momentum. We can't take some of this and change it into some of that. It can't be done. This becomes, students are more likely to make this mistake once we start talking about conservation of energy. And you know that you can convert kinetic energy into potential energy and vice versa. So it might become tempting at that point to think, well, maybe momentum can be converted the way that energy can. Maybe I can convert x momentum into y momentum, but we're stating definitively here that you cannot. They are separately conserved. X momentum stays constant and y momentum stays constant. You can't turn one into the other. So here's a question that I'm going to ask you to think about. I'm going to ask you to pause the video in a moment, come up with your answer. Question is, if the initial momentum of a system is given by this vector, so this magnitude in this direction, if that's the initial momentum of the system, and it is being conserved, then which of the following, of this list of vectors here, which of the following could be the final momentum of the system, say after a collision occurs? If this is the initial momentum and it's being conserved, which of these could possibly be the final momentum of the system? Please circle all that apply, all possibilities. Pause the video now. You got it? Okay, well I hope you recognize that this is the only vector that's identical to that, so this could certainly be the final momentum of the system. The next two show that the magnitude has changed. That one increased, that one decreased. So those cannot be the case. If momentum is conserved, we can't have a different magnitude at the end. But these others, the next seven, all have the same magnitude as the original momentum. So does that mean that these could be the final momentum? Could we just take this initial momentum and tilt it while conserving the magnitude? Is it magnitude that's conserved? And the answer is no. None of those are possible. Because when we say that a vector is conserved, we mean its magnitude stays the same and its direction stays the same. That's actually what this is stating. If the x component stays the same and the y component stays the same, that means the direction of the vector will stay the same. You can't reorient the vector. So only this vector here is equal to the original vector. So if momentum is conserved, this has to be the final momentum as well. It cannot change direction. It must have the same magnitude and the same direction.